I want you to do something for me right now. Look at your hand.
Okay.
Seriously, just hold it up and look at it. You see skin, knuckles, maybe a hangnail. But if we zoom in, and I mean really zoom in, what are we looking at?
Carbon, hydrogen, oxygen.
Just atoms. Mindless, dead atoms buzzing around in a void. They don't have thoughts. They don't have feelings. They don't know they are part of a hand.
We certainly don't wonder about their own existence.
Exactly. But somehow, when you stack enough of those mindless, dead atoms together in a very specific configuration, you get you. You get a mind. You get the ability to look at that hand and ask, how did this happen? So the mission for this deep dive is to figure out how we bridge that gap.
Right.
How does quantity, just adding more dead stuff, suddenly transform into quality, a living mind?
It is the ultimate alchemy, isn't it? It's the fundamental paradox of the universe. And the framework we're using to solve this today is emergence.
Emergence.
Now, I know when people hear that word, they often think of it as a buzzword, or worse, a get-out-of-jail-free card for things scientists simply don't understand yet.
It does sound a bit like magic. Step 1, atoms. Step 2, complexity. Step 3, consciousness. Ta-da.
And our goal today is to dispel that magic vibe completely. Based on the stack of research we have covering everything from 19th century philosophy to statistical physics and the bleeding edge of AI, we're going to see that emergence isn't fairy dust.
It's a real thing.
It is a rigorous structural necessity of nature. It's the reconciliation of two contradictory ideas.
Which are?
Micro-level dependence and macro-level autonomy.
Let's unpack those immediately, because that definition seems to be the anchor for everything else we're going to discuss.
It is.
Micro-level dependence seems pretty obvious. You can't have a traffic jam without cars.
The whole depends entirely on the parts. If the cars vanish, the jam vanishes. There is no ghost jam left behind.
Sure.
But the second part, macro-level autonomy, is where it gets counterintuitive. The traffic jam has properties that the cars do not. For instance, a traffic jam can move backward down a highway.
Right. The wave of brake lights ripples back.
While every single car is moving forward, the jam is a real entity with its own behavior, its own rules of movement, distinct from the drivers who are just trying to get home.
That is a great image to hold on to. The jam is a thing, even though it's made of things that aren't jams.
Exactly.
So people must have been scratching their heads over this for a long time. Where does the formal history of this idea actually start?
I mean, it goes back to the beginning. Aristotle had an intuition about it. He argued that incremental changes could lead to a sudden qualitative shift.
But not with the same words.
No, if we want the real vocabulary, the toolkit we use today, we have to go to the Victorian era. Specifically, a philosopher named George Henry Lewes in 1875.
Lewis is interesting because he was writing right when the scientific world was trying to figure out if chemistry and biology were just physics in disguise.
He drew a line in the sand.
Yeah.
He distinguished between resultance and emergence. A resultant is additive. If you have a sandbag that weighs 10 pounds and you add another 10-pound bag, you have 20 pounds. It's predictable. It's linear.
It's just simple math. 1 + 1 = 2.
You don't need to see it happen to know the result. But an emergent, Lewis argued, is qualitatively different. It defies that additive logic.
How so?
You can't look at hydrogen, a gas that fuels fire, and oxygen, a gas that feeds fire, and mathematically predict water, which extinguishes fire.
No, you can't.
Wetness is an emergent property. It's a novelty that appears only when the parts combine.
It seems like that distinction kicked off a massive intellectual war in the early 20th century. The British emergentists.
It sounds like a very polite but intense indie band.
It really does.
A very intellectual band. Thinkers like C.D. Broad, Samuel Alexander, and Lloyd Morgan. They were trying to navigate between two extremes that dominated science at the time.
What were they?
On one side, you had the mechanists or reductionists.
The we are just wet robots crew.
Right. They believed biological life is just moving particles, end of story. Nothing to see here.
And on the other side?
On the other extreme, you had vitalism. People like Hans Driesch, who looked at how complex an embryo is and said, physics can't explain this. There must be a vital spark, an entelechy.
So basically a soul, a ghost in the machine that tells the cells what to do.
Exactly. And the emergentists said, we don't need a ghost, but we also aren't just robots.
A middle path.
They argued that when matter gets complex enough, it generates transphysical laws. Nature builds its own ladder. You get new levels of reality, chemistry, biology, psychology that follow their own rules without violating the physics below them.
That sounds like a nice middle ground. But in the modern literature we have today, it seems scientists realized emergence isn't just one thing. We have to split it up.
We do. We have to distinguish between weak emergence and strong emergence. And this is where the rubber meets the road for our understanding of reality.
Okay, let's start with the innocent one, weak emergence.
Weak emergence is metaphysically innocent because it fits perfectly with our understanding of physics. It says that novel patterns arise from complex interactions, but, and this is the key, they are fully caused by the underlying rules.
The classic example in the notes is Conway's Game of Life.
Yeah.
And for you listening, this isn't the board game with the little plastic cars. It's a computer simulation.
Right. Imagine a giant grid, like an infinite chessboard. Each square is a cell that is either alive on or dead off.
And the rules are super simple.
Incredibly simple. Things like, if I have 2 neighbors, I stay alive. If I have too many, I die of overcrowding.
Just simple binary logic.
Yes. But when you run the simulation, you see these massive, complex structures form. You get gliders that travel across the board. You get guns that shoot other patterns.
And if you just looked at the code, the simple rules, you would never predict a glider. It's unexpected.
And here's the catch. It's not magic. If you have enough time, you can trace exactly why the glider happened.
Huh.
Precisely. And this leads to a concept by the philosopher Marc Baudot called explanatory incompressibility.
That is a mouthful. What does it actually mean?
It basically means there is no mathematical shortcut. You can't write a clean formula to predict where the glider will be in a billion steps.
You have to do the work.
You literally have to run the simulation step by step to find out. The outcome is determined, but it's only knowable through the process. That is weak emergence.
So it's surprising, but still predictable in principle.
It's surprising, but it's deductible if you do the work.
Okay, so weak emergence is like baking a cake. You mix the ingredients, you get something new, but it's all chemistry. We understand it. Now let's go to the deep end. Strong emergence.
This is the radical claim.
It is.
Strong emergence suggests that there are high-level phenomena that are not deducible from the low-level, even in principle.
Even if you had a computer the size of the universe.
Even then.
And the poster child for this is us.
Specifically, consciousness. The philosopher David Chalmers calls this the hard problem. You can map every neuron, every ion channel, every electrical spike in a brain, but nowhere in that map do you find the feeling of seeing the color red.
The experience of it.
That subjective experience, the qualia, seems to be something that sits on top of the physics, not inside it.
And if strong emergence is real, it implies something called downward causation, right? Which sounds like it breaks physics.
That's the controversial part. In physics, causation flows up. Atoms hit atoms, making molecules move, making cells move.
On up.
But downward causation suggests the whole can push the parts around. That my thought, a high-level mental state, can cause a neuron to fire.
Which is weird, because if physics is a closed loop where atoms only listen to other atoms, how does a thought push an atom?
Exactly. It implies the rules of physics as we know them might be incomplete.
Okay, we're getting very philosophical, and I want to ground this. We've talked about the what, but I want to know the how. How does nature actually do this? How do things lock together to form these new layers?
This is where we leave philosophy and enter hard physics. To understand emergence, you have to understand symmetry breaking.
Okay.
The classic example is a magnet. Imagine a block of iron. Inside, it's full of atomic spins, like tiny compass needles.
And at high heat, they're going crazy, right?
Yeah.
Spinning randomly.
It's chaos, but it's symmetric chaos. There is no preferred direction. The average spin is 0. But as you cool that iron down, you hit a specific point called the critical temperature, or TICO. Exactly.
Right.
Snap. Suddenly, vast numbers of spins lock into alignment. They all point north. The metal becomes a magnet.
Wow.
Now here is the emergent insight. That magnetism, what physicists call the order parameter, doesn't exist in any single atom. It is a collective property.
But the wildest part of this, according to the physics notes, is something called universality. And I need you to explain this because it sounds like it shouldn't be true.
It is one of the most beautiful discoveries in physics. Scientists used a mathematical tool called the renormalization group to study these critical points.
Right.
They found that if you look at a magnet aligning, and then you look at a completely different material like water turning into steam, the math at that critical transition point is identical.
Wait, hold on. Boiling water and a cooling magnet follow the exact same rule.
At the moment of transition, yes. The exponents in the equations are the same.
That's wild.
This is profound because it proves that emergent laws are substrate independent. The organizing principle doesn't care if it's organizing iron atoms or water molecules.
The microscopic details wash out, and only the macroscopic pattern remains.
Precisely.
That suggests that organization is a force of nature in itself. It's not just about what things are made of, it's about how they relate.
Correct. Structure matters as much as substance.
Speaking of structure and substance, let's pivot to the place where we are watching emergence happen in real time right now. Artificial intelligence.
Yes.
Because these large language models, LLMs, feel like the ultimate laboratory for this.
They really are. We are building massive statistical engines, and we are seeing properties emerge that we didn't explicitly program.
It's the closest we've come to creating a synthetic brain. The papers talk about scaling laws. The idea that as you make the model bigger, more data, more compute, it gets smarter. But it's not a smooth line, is it?
Not always, and this is where it gets spooky. The training loss, which is just a measure of how many errors the AI makes, usually goes down smoothly. But specific capabilities, they show elbows.
The elbows.
Sharp, sudden turns. Imagine you are training an AI to do arithmetic. For a long time, the model is just guessing. Its accuracy is near zero.
It's random.
It's random. Then you add a little more computing power. Say you cross a threshold of 10 to the 22nd FLOPs, and boom.
It solves it.
It jumps from 0% accuracy to near perfect. It's a phase transition, just like the magnet. And recently, researchers have identified a mechanism for this called grokking.
I love that they use the sci-fi term from Heinlein, right?
Yeah.
To understand something so thoroughly, you become one with it.
That's the one. In AI, grokking looks like this. You train a model. At first, it memorizes the training data. This is called overfitting.
Right.
It's like a student cramming for a test by memorizing the textbook answers without understanding the math. If you give it a new question, it fails.
So it's faking it. It's just parroting.
It's faking it. But, and this is the crazy part, if you keep training it way past the point where it seems reasonable, something clicks inside the black box.
What happens?
The validation accuracy suddenly jumps to 100%.
What is happening physically inside the code? What changed?
We call it circuit reorganization. The model literally rewires its internal connections. It switches from memorization circuits to generalization circuits.
It finds a rule.
For example, in math tasks, it might stumble upon a trigonometric identity that solves the problem efficiently. It stops memorizing and starts understanding the underlying rule.
That is an aha moment. It's literal insight emerging from brute force repetition.
It implies that if you pressure a system enough with data, understanding is simply the most efficient way to compress that data.
Emergence is an efficiency hack.
In a way, yes.
That is a fascinating way to put it. So we see this in magnets, we see it in AI, but I want to bring it back to the biological. Because human development feels like a series of these moments.
Absolutely. And here we should distinguish between synchronic emergence, which is vertical, happening at the same time, like the magnet,
Right.
and diachronic emergence, which happens over time.
Like evolution or growing up?
Take the birth of agency in infants. A newborn doesn't know it's a person. It doesn't know it has hands. It certainly doesn't know it can control them.
It's just a bundle of reflexes and noise?
Right. But notice the feedback loops. A baby waves its arm randomly. Pure chaos. By chance, the hand hits a toy hanging above the crib.
Okay.
The toy moves. The baby sees the motion. This creates a loop. Proprioception, feeling the arm move, links to vision, seeing the toy move.
Wait, I did that.
Eventually, yes. The coordination dynamics self-organize. The random waving collapses into a targeted reach. The concept of a causal self, an agent, emerges from the chaos of motor reflexes.
That's beautiful. The self isn't there at the start. It's built by interacting with the world.
And this scales up to the social level. Look at language. You and I are following complex grammatical rules right now. Subject, verb, object. Did we invent those? Did a committee design English?
My high school English teacher acted like she did, but no.
It feels designed, but language is a collective achievement. It starts with meaning pointing at a mammoth, then lexicalization, a sound for mammoth.
But grammar.
But grammar, syntax, that emerges because of constraints. We need to reduce ambiguity and save cognitive energy.
So grammar is a desire path. It's the shortcut the group found over centuries.
Precisely. It's a diachronic emergent, a structure that exists to serve the collective, which no individual could have built alone.
Okay, we built a pretty towering edifice here. Magnets, babies, chatbots, all self-organizing. But we have to address the elephant in the room. The reductionists.
Yes.
Because they are listening to this and rolling their eyes.
They are, and they have valid points.
They would say, look, this is all poetry. The traffic jam isn't real, it's just cars. If you track every atom, you explain the whole thing.
This is the hard-nosed ontological reductionism, and they have a heavy hitter on their side. The philosopher Jaegwon Kim.
Okay.
He formulated something called the causal exclusion argument. It is a logic trap designed to kill the idea of strong emergence.
Walk us into the trap.
Yeah.
How does he argue that mind doesn't matter?
Kim says, imagine you raise your hand. That is a physical event. It has a sufficient physical cause, neurons firing, muscles contracting.
Right, physics works.
Physics is complete. It leaves no gaps. So Kim asks, if the physics is sufficient to move your hand, what is left for your mind to do?
I see the problem.
If the atoms do all the work, adding a mental intention is redundant. It's what philosophers call overdetermination.
It's like two people pressing the same elevator button at the exact same time. He didn't need the second person.
Right. And Kim argues that nature doesn't do redundancy. So your mental state is either impotent, it's just the exhaust fumes of the brain, or it doesn't exist as a distinct thing at all.
That is bleak. It basically says our sense of agency is a delusion.
It is a stark view. But the emergentists have a defense. They use a concept called macresis.
Macresis. That sounds like a villain in a Marvel movie.
It's actually from the Greek. It refers to the idea that the whole constrains the parts. It doesn't violate physics, but it shapes the possibilities.
Wow.
Think of a wheel rolling down a hill.
Okay, I'm picturing a tire.
The atoms in the rubber tire are moving in a cycloid pattern, a specific curve, y. Not because the individual atoms decided to move that way.
No.
But because they are locked into the structure of the wheel. The global structure determines the trajectory of the parts.
So the structure has causal power. The atoms have to go where the wheel goes.
Exactly. The reductionist says the atoms move the wheel. The emergentist says the wheel steers the atoms. Both are true.
It's a two-way street.
It's a two-way street. The whole limits the freedom of the parts, and in doing so, creates new behavior.
So where does this leave us? We've gone from the symmetry breaking of cold iron to the aha moments of AI to the very structure of our own agency.
I think it leaves us with a necessary shift in our worldview. For the last few centuries, science was obsessed with the bottom, finding the God particle, the theory of everything.
The ultimate equation. If we just smash the particles hard enough, we'll find the answer to the universe.
Right. But emergence suggests that the bottom isn't where the most interesting action is. The action is in the pattern formation. It's in the way quantitative changes. Just adding more heat, more neurons, more data suddenly snap into qualitative shifts.
It's humbling. It means that even if we know the rules of the parts perfectly and we know physics pretty well, the behavior of the whole can still surprise us.
It remains perpetually novel. We can know exactly how a transistor works and still be totally baffled when the AI learns to write poetry.
Right.
We can know how a neuron fires and still not understand a thought.
And that tension between the rigid, boring rules of the parts and the unpredictable, creative behavior of the whole is exactly where we live.
That's the sweet spot of reality.
Here's a final thought for you to chew on. We've talked about neurons creating a brain and individuals creating a society. If emergence is real and new layers of reality form when things get complex enough, are we the top layer? Or are we just the parts of something bigger that we can't see yet, just like a neuron doesn't know it's part of you?
Now, that is a question worth asking.
Thanks for diving deep with us.
Keep looking for the patterns.